Hello there. We continue with the demo session now. Zeynep Işık and Mert Pekey will give the demo session. So maybe I will introduce them. I can introduce them briefly. Zeynep holds a BSc degree in computer engineering program from Boğaziçi University, and she is now currently pursuing a master's degree at Sabancı University. Mert holds a BS degree in computer science and engineering from Sabancı University and is currently pursuing a master's degree there. So, Zeynep, if you are ready, we can start.
Thank you so much. In this session, I will show you how to use protein language models on phosphorylation prediction task. In this task, we will train a simple neural network by using distinct protein representations, including one-hot encoding, Broadweg representation, Broadbird, and ESM2 embeddings. The aim is to predict if a given sequence is phosphorylated or not. So this is a binary classification task. During the session, we will first see how to represent the protein sequences, and then we will train a two-layer neural network, and in the final, we will evaluate our predictors. Okay, these are the libraries that I will use in this session for different purposes. Okay, here is about data. Data is provided as phosphorylation data.csv. Here, we collected the phosphorylated data from Phosphocyte Plus, phosphorylated peptides from Phosphocyte Plus. Phosphorylated sequences are provided as 15 long peptide sequences, and in the middle position, there's phosphorylated residue, phosphorylated amino acids. Actually, there is no experimentally proven unphosphorylated data, so we prepared our data for unphosphorylated samples. We followed these steps. We know the phosphorylated peptide and the phosphorylated residue. In the same protein, we found another residue which is the same type with the phosphorylated residue, and we combined that residue, another residue, with seven peptide sequences from left and the 7 peptide sequences from right, and then we created unphosphorylated peptide sequences which are not reported in Phosphocyte Plus, and these steps, while following these steps, we followed the literature actually. Actually, in our original data, we have almost 300,000 phosphorylated, unphosphorylated pairs, but for learning purposes, we took a sample of 5,000 positive and negative samples. This is the small portion of phosphorylation data. Site is positive samples, phosphorylated samples, and non-site means unphosphorylated samples. Okay, here I will separate the positive and negative data and create its labels. Okay, now in task 1, we will prepare protein representations. We will prepare protein representations in different ways, including one-hot encoding, Broadweg, Broadbird, and ESM2 model embeddings. Here, in order to show you step by step, I took 2 peptide sequences. First of all, one-hot encoding. Here, each amino acid is represented as one-hot vector according to the index in predefined amino acids string. Some peptides contain gap, which is shown as underscore, and if a peptide sequence contains gap, the corresponding vector for gap residue will be represented as 0 vectors. Okay, here this method is for one-hot encoding. Initially, we have a 0 matrix, and if we see a gap, then we will not change anything. But if we see an amino acid in the amino acid strings, then we will first find the corresponding index of amino acid, and then we will put 1 in the position of it. So in the end, we will concatenate the 1 hot vectors, and we will get a 300 long 1 hot encoding. I will run the cell and you can see the representations. These are the sample peptide sequences, and this is the 1 hot encoding representation. Okay, the second representation, second baseline representation is PROTVEC. As Öznur Hoca said, PROTVEC is a skip-gram model. Each consecutive 3 grams are represented as a 100-dimensional vector, and these are recalculated. You can see these are the amino acid combinations of 3 grams, and these are the corresponding pre-calculated embedding vectors. Okay. Here there are some methods. These methods read the pre-calculated embeddings. This method gets the consecutive 3 grams in a given peptide sequence. This method is for padding. Again, if a sequence have, if a 3 gram has gap sequence, we will put 0 vector for it, and for the other 3 grams, we will get the sequences from the calculated dictionary. Okay. Grams, and we will put the sequence if it has gap. Okay, back mat. And now I will show you the embedding. Sorry, I think there's a message in the gap. In the chat, sorry. Okay. Okay, this is the and the representation of protein, and the length of the encoding is 100. Now, transformer-based representations. PROTBERT is one of the protein language models which is trained on mass language modeling objective. It encodes the information by protein sequences such as protein function and protein secondary structure. This model has own tokenizer, and each tokenizer have rules how it accepts the input sequence. That's why for transformer-based models, we need to pre-process the input sequences. Okay. Before using the model, we need to load from Hugging Face, from retrained, and model name. And since we will run the code on GPU, we need to load this to CUDA device, and we need to load the tokenizer again from Hugging Face. Okay. The input format of the PROTBERT is a little bit different. For example, for a given sequence, PROTBERT tokenizer accepts sequence if all of the amino acids are uppercase. There should be spaces between them. Some amino acids is not known by PROTBERT tokenizer. That's why we need to change them with X unknown residues. And we need to change gap representation from underscore to dash. There are, as I said before, each tokenizer has its own rule. That's why if you use protein language models, you need to read the model definitions and the model using, how you model cards. Okay. These amino acids are not known by PROTBERT tokenizer. Now, I will first uppercase this and then add spaces between them, change these amino acids with unknown, and I will replace the underscore representation of gap to dash. Okay, and now we will apply the same things to second sample. Okay, now you can see this. Uppercase spaces and gap representations are changed. Okay. For transformer models, before giving the input to the model, there's a intermediate step. This is the tokenization. We need to tokenize the pre-processed amino acid sequence, peptide sequences. So we will give the pre-processed peptide sequences to the tokenizer. Tokenizer is like digitizing the input sequences, and in the output you can see this. Each amino acid residues are converted to a number representation. Okay, in the beginning and end of the input representations, there is a CLS token embedded, there is a CLS token, and there is a end of sentence token in order to separate the sequences. Okay, now final step in the extracting embeddings. We will give the tokenized version of the sequences to models. Since our model is in the CUDA device, we need to, on the GPU, we need to send it to GPU. Okay. The output of the last hidden state is the representation of the given input. Okay. Now, since it is high dimensional, it may create problems during training, because if you have depending on your computational resources, actually. But you can use the there are other ways to represent the protein language proteins after getting the output. For example, this is, last hidden state output is the whole matrix. You can see the size. For each residue or for each token, there is a 1024 dimensional vector, and this whole matrix is really huge. But you can represent your input sequences by getting the CLS token embedding. CLS token embedding is like the summary of your input sequences. You can simply take this like first row, and you can get the column-wise average of the matrix, and this is also another way to represent your input sequence. Okay. Now ESM2 is the our final model. ESM2 is the newer model compared to ProtBird. It encodes the information, including structural characterization. It has its own tokenizer as well. Here, model loading steps are the same. The tokenizer's acceptance rule is simpler and straightforward. The sequences must be uppercased, and again, gap sequenced must be represented as dash, not underscore. Sequences must be uppercased, and again, we need to apply the same thing for gap sequence. Okay, now these are the pre-processed versions of our inputs. Again, before giving the inputs, before extracting the embeddings, we again need to encode the pre-processed inputs and get the tokens. We get the tokens and feed to the model. Okay. Embedding dimension size differs model by model. For example, embedding dimension of ESM model, actually here I use ESM model 6 million parameter version. That's why the dimension of the embedding is lesser than ProtBird. For each amino acid, there is a 300 20-dimensional matrix. Here again, you can use the whole matrix embedding or CLS token embedding or average of the embeddings, and you can see the size differences. Okay, this is the average. Now we will use, until now we learned how to represent the input peptide sequences in different ways, and now we will use the embedding, we will use the representations in order to train a neural network. Before starting, I will combine the positive and negative data samples, and I will divide the data into train, validation, and test sets. Okay. Here, there will be two distinct predictor classes because processing the data and feeding to the model steps are different in baseline approaches, I mean one-hot encoding and PROTVEC, and the transformer-based approaches, including PROTBERT and ESM2. This is for baseline predictor. It takes input size as an input. This is simple two-layer network. Okay. Let me run this. And this validation loop is for, again, baseline encodings. It encode the, it take the parameters like input size, train encoding, train labels, validation encodings, validation labels. I keep batch size, number of epochs, and the learning rate fixed because of the time constraints, but you can play with the parameters and you can experiment this. First of all, before training the predictor, we need to define a phosphorylation predictor and give the input size. Okay. We need to define the loss and define the optimizer. During training, we will model take the input batch by batch. This part is calculating batches during the training. Okay. In order to get the outputs, we will give the train encodings to predictor, and after completing this learning step, then we will create the we will calculate the loss. This is important. This is important in updating the predictor weights. Okay, this is the backpropagation step, and in the end of each epoch, we will use validation data to get the validation results. In order to use the predictor in validation mode, we need to open validation mode. In validation mode, we will not change the weights of the predictor. Okay, and input is validation encodings, and we will give validation encodings to predictor as an input. After training ends, we will plot the learning curve for validation and train losses. Okay. Now we will write a predictor for a protein language model representations, and we will write a train validation loop. Here, the difference is we need to give protein language model as a parameter because we will because we did not okay, let me say in this way. We give this because we will extract the embeddings during training. Okay, we will give the PLM model and input size as a parameter. During the forward loop, we will get the embeddings. In order to do this, I will freeze the weights of protein language model. Because we will not train protein language model, we will try to training a predictor. Okay, we will freeze the weights of the protein language model, and we'll give the pre-processed input to the model. Okay, after getting the embeddings, we will get the last hidden state because it keeps the encoding, it keeps the embedding matrix, and As I said before, we will use the CLS token embedding, which corresponds to first row of the embedding. Okay, this is our predictor for protein language model embeddings. Okay, now most of the part is the same, but I want to show you the difference in training loop. In the previous training validation loop, I mean for the baseline, we directly give the encodings to the model, but for protein language model, we give the preprocessed version of the data, and then we tokenize it. There's an intermediate step. So since I want to show this, I add this step to this method. This is the training batch, and we give the training training sequences to preprocessed training sequence to tokenizer, and get the tokens. And we will and in the final we will give the tokens to predictor. Okay, it is in the CUDA device. Okay. Other steps are the same. Loss calculation, backpropagation, I mean one of the learning steps, evaluation mode, and the validation. Okay, this is for the learning curve, plotting the learning curve. Okay, now we are done with the writing predictor classes and the train validation loops. Now we will train our models one by one. One of them is the one-hot encoding. For each sequence in training data, I will get the one-hot encoding of the sequences. Oh, sorry. One-hot encoding of the sequences, and same for validation data. And now we will put the parameters. Our model is one-hot encoding. Input size is 300, and the other parameters are train encodings, train labels, validation encodings, and validation labels. Okay, let's train this. I hope not to get an error. Sorry, labels. I need to check this. Sorry, labels, train labels. Okay, go back to training. Okay. Training is very fast. Okay, in this plot you can see this R2-layer neural network, I mean predictor, is learning from one-hot encodings, and model training time is 4 seconds. Now we will prepare prospects for each sequence from the predefined trigram vectors, and this is the same for validation data. Here I want to show you the parameters implicitly. Model is PROTVEC. This is the input size of the PROTVEC embeddings, train encodings, train labels, validation encodings, and validation labels. Let's train this. Okay. Again, you can see this. The model is learning from PROTVEC embeddings. Okay, now last two training models. Okay, for the transformer models, we first need to preprocess the data, change unknown amino acid. By the way, these amino acids are unknown by tokenizer. Okay, and uppercase replace underscore representation of gap with dash. Okay, let me copy and paste because it is the same for validation data. Okay, for the train validation loop, our model name is, Rothbard. PLM model is Rothbard model. Tokenizer is Rothbard tokenizer. Train data is preprocessed train data and train labels, and validation data is preprocessed validation data and validation labels. Okay. Oops. One required validation. Sorry. One is missing. Validation. Let me check. Validation labels. Tokenizer. Input size. Sorry. 1024. Okay. Training will start. It may take time because the embedding size of Protbird is huge. It is 1024. The size of embeddings can be also a sign of how big the model is. We will see in the next step ESM2 version train, ESM2 8 million parameter version training is very fast compared to Protbird because its embedding dimension is almost 1/3 of Protbird. Protbird is not the only model in the paper that presents it. There are more models. Some of them use different architectures like T5 architecture and different objectives like causal language modeling. This is the same for ESM models family. There are a lot of ESM models. Each of them is specialized on different tasks, and each of them have some different parameters, some of them small models, some of them large models, and objectives and the training data may differ between transformer models, even in the same model family. Okay, the last step. We can see this, the model is learning from the Protbird embeddings. Last embedding is ESM2. I will prepare the inputs, uppercase, and change the gap. Uppercase, and change the gap representation. Okay. Now I put the parameters beforehand. ESM2 8 million parameters, ESM model, ESM tokenizer, input size, preprocessed train and validation data, and the labels. Okay. The training time compared to Protbird is less and the training is fast. We can see the learning again here. Last step is evaluation. In this section, we will evaluate each trained predictor on the test split. There are small differences in evaluating test sequences between baseline method and protein language model representations. I will not prepare the test data from scratch, so I will just run this cell. Here for the evaluation, we again open the predictor as predictor in the evaluation mode, and we will not change the weights of the predictor. We will take the test data batch by batch. We will give it to the representation. I want to show how to evaluate your model. After getting the outputs from the predictor, you need to give this the softmax. Softmax method is converting model output to the probability. And probability means how probable your class is belong to a true class. Okay. And after calculating probabilities, you need to convert this to class labels. Sorry. Class labels. And after getting predicted classes, we need to compare labels, and for giving them to evaluation metrics, we need to get the correct number of predictions. Okay. In the evaluation, we will evaluate our predictors by considering accuracy to measure the percentage of correctly classified samples, and a F1 score to measure how well the model handles both false positives and false negatives, and a UC score to assess the model's ability to distinguish classes across various thresholds. Okay. This is for baseline evaluation, baseline models, baseline representation evaluations, and this is for a protein language model representation evaluations. The only difference is we will take inputs as pre-processed and we need to tokenize the test data. Okay, I hope I didn't forget any space. Okay, I am sorry. Outputs, sorry, typo. Okay, this is the product result. This is the birth result, and this is the ESM2 results. Okay. You can see this one-hot encoding gives the best result. It may happen because of various reasons. Since our data is limited, complex approaches may not generalize the data. Secondly, predictors may be trained higher number of epochs, or we can search better parameters. In conclusion, the phosphorylation prediction task is to be better. Okay, you can play with the parameters, and hyperparameter search also helps you to improve your model predictions. Okay, this is all what I said. I hope this is a beneficial demo for you. Thank you for listening.
Thank you, Zeynep. I think there are two questions maybe I can direct to you, Zeynep.
If it's okay, I can answer by typing while
Sure.
presenting. Okay.
Mert, please continue.
Hello everyone, and now I will talk about how to fine-tune these protein language models. So Zeynep used the pre-computed embeddings so that her model only learns the last classifier layer, which is very small actually. But you can also change the parameters of your protein language model itself to make your model more specialized for your downstream task actually, because the protein language model gives you the generalized representation of the proteins. It knows a lot of things about the proteins, but for your downstream task, you may make it more specialized for that. And for this one, we will use PyTorch again and transforms library for the model. And also I will show you how to use the trainer. Zeynep showed you the custom PyTorch training loops that you get your data and feed it to the model and update your parameters. But also Hugging Face gives you an easy to use interface so that you can easily give your model and data and some parameters. So if you know what you are doing, the code part is very small and it will just train your model easily. And also at the end of this, I will show you how to use LoRa, which is a parameter efficient fine-tuning technique using the Hugging Face PEFT library. So I'm just skipping the data part because we are going to use the same data set as Zeynep used so that we can compare the results. So we are expecting these fine-tuning all of these 8 million parameters increase the model performance because specializing our model actually. I'm just skipping the data creation part, and we are now creating our data sets, which are a PyTorch dataset class. The PyTorch dataset class is a class which helps us to get the data randomly in the training, and it also helps us to get data in batches very easily, so that we can, for example, in every iteration, we can get 128 data. So I want to show you the one thing about Hugging Face models, so that they have different type of model types actually, and some of them are for some tasks. So Zeynep used the ESM model, which can be seen as a feature extractor model. It's a base model and creates the embeddings of the. If you give your sequence, amino acid sequence to it, it gives you the embedding. And she added a classifier layer at the end and trained that classifier layer. You can also do this. I mean, when I just print the ESM model, you can see the architecture here. And here at the end of this part, you will get the embeddings, and you just send these embeddings to a classifier and learn that classifier, but you are not changing this model. But if you want to update also the model parameters by fine-tuning, you can just again manually create a classifier layer and add here, and also make all of your model trainable, and also define loss functions, etc. But Hugging Face gives you the opportunity that is specialized for the classification tasks, because we are doing binary classification right now. We can directly use ESM4 sequence classification model. The only difference is when you set your number of labels here, and then I just print it automatically adds a classifier layer at the end, which outputs two different predictions. So the phosphorylates or non-phosphorylates, and you don't need to manually create and add them. And also it automatically calculates the loss value for you. So you don't need to again manually calculate that loss. So we are going to use this one for now for our fine-tuning part. And we are going to update all these parameters for our downstream task in the first part, which is called full fine-tuning actually. And yeah, I will use trainer as I said, but I have added the custom PyTorch training loop to compare how long the code is. And they are doing exactly the same thing, but trainer is an easy-to-use interface. And it expects us some arguments actually. And the most important thing is model itself, of course. We are just creating our model from Hugging Face, and we need to set some training arguments, because we can change the training by setting these arguments. And as you know, there are some arguments, important arguments, such as learning rate, batch sizes, and how many epochs do you want to train this model. I just set it 10 for this demo purpose. And also it helps us all of the saving operations. If we set save strategy equals to epoch, at the end of each epoch, it will just save the model checkpoint file into a directory it will create called results in our directory, project directory. Also, if we set evaluation strategy equals to epoch, at the end of every epoch, just takes the validation data and evaluate the performance on the validation data, so that during training, we can also see the validation performance. And there are lots of arguments in the Hugging Face training argument class. So maybe 50 or more than 50. If you don't define them, they use the default values in them. Also, I mean, you don't need to set any compute metrics function. And if you just run your trainer using model and arguments, it will just log and print the loss values during training loss and validation loss. But if you want to see the accuracy change or F1 score change during training, you can create a function, and this function takes an argument. This function is automatically be called by the trainer, so that it has some formats. So it will take an argument. This argument will have predictions, logistic predictions, and the labels itself. And Hugging Face trainer just send these arguments to this function. And you will calculate your metrics actually. You can calculate your metrics whichever way you want. I just used scikit-learn library. And you just return a dictionary. I also plot the training curve during training. So we can now initialize our trainer. As I said, it expects model, arguments, of course, our data sets. And if we want to see other metrics, we can give a function which computes the metrics. So there are two important methods in the trainer. One is .train actually. It will train the model. And let me run it, and during this training, I can explain the other method, which is evaluate method. So evaluate method does not update your parameters, but just make predictions on these data sets. I mean, during training, it will just, because we have set the evaluation strategy equals to epoch, at the end of each epoch, it will automatically call the evaluate method on the validation data set, because we give the validation data set to the trainer, and we can see the validation performance as well. And rather than just the loss values, we can also see other metrics because we have set the compute metrics function. So as you can see, this little bit overfits. Our data is not that big for these kind of models because we are fine-tuning an 8 million model. I mean, it's the smallest ESM architecture, but for this data and for this task, this may be a little bit bigger model. And let's look at the test performance. Yeah, on test set. So as you can remember, Zeynep, when she tried to train the classifier on the pre-computed embeddings, she get 70% of accuracy. But now we have almost 93% of accuracy and F1 score on the test set, so that the fine-tuning protein language models for these downstream tasks have a lot of performance improvement here. So as I said, we have done all of the same operations that we done here using custom PyTorch loop. I'm not go on it. Zeynep did actually, but I just show you how it increases the code you need to write, and you need to set a lot of actually settings to train it correctly. So that here now we don't have a train function in the trainer class. We need to write it on our own, and we need to calculate the training and update the parameters by ourselves, and also create an evaluate function to make evaluation on validation data and test data, of course. The performance is a little bit similar, but a little bit different because, as I said, training arguments have some default argument that we didn't set, but it uses that defaults, so that the results little bit change, but mostly similar. Yeah, you can see the validation curve, and yeah, in this part it gets 94% of accuracy, a little bit similar and higher than before. So I want to go over the LoRa part, so that we have fine-tuned all of these ESM2 model, 8 million parameters. But sometimes these models are very big. So they are so large that, and we cannot store them in a GPU. And I mean, GPUs are very expensive. If you don't have an access to a larger GPUs, or if you don't have an access to servers, you cannot fine tune them, and this is expensive. Also, you can also think it like that when you train these, they all have a carbon footprint, and in the sustainability viewpoint, the fine tuning for a lot of downstream tasks have bad environmental effect as well. So we can fine tune our models and get the similar performance just by training smaller parameters. As Öznur Hoca told, LoRa is a parameter efficient fine tuning techniques, and it freezes out all of these parameters, model parameters. So original parameters not going to change, but we have inject some small trainable low rank matrices, and we are going to train them only. So this means we need to change some model architecture, but Hugging Face PEFT library does that for us. So we will use it, and this is very easy actually. So as before, we are going to initialize our model, the original model, and we need to set a LoRa configuration because it has some configurations we can change. You can think some of them as hyperparameters also, and we will define LoRa configuration and call get PEFT model function. This will take our model and this configuration and convert our model to LoRa model actually. And the most important thing is rank, because these matrices have rank, low rank matrix, and we can define which rank they have. And this is also one of the most important hyperparameter here. And one of the other most important part is target modules. So usually LoRa is applied to linear layers, and we need to define which linear layer we want to apply to LoRa. So let's look at the model architecture, not the LoRa model, but original model architecture. I'm just going to print it. Yeah, we have seen it before. This is our model architecture, and they define some names. The meta actually, when putting it in the Hugging Face, define names to the layers, and some linear layers we can see. I mean, query key value layers in the attention part, and some dense layers also LoRa can be applied to them. Now we will apply LoRa to just only the query key and value parts, not to dense parts, but this is also increase the number of injected LoRa layers as well. Yeah, for example, let's first apply LoRa to only query parts. So this is the original model. The query has a linear layer. By the way, there are 6 ESM layers, but because they all have same architecture, it just summarizes for us all the 6 ones. Let's look at the LoRa converted version. So as you can see, key and value are still linear layers, but query layer is changed with LoRa linear. So it has a base layer, which is the original model layer. So we know that original model parameters are not going to be updated. So this is frozen. But the only thing we will train is this LoRa A and LoRa B, which are the low rank matrices. And because we have we set the rank as 16, you can see that their rank are 16 here. So if we just change it to key and value as well, we can see that key part and value part are changed as well here. This uses regex to match the names, so that sometimes, I mean, you need to look for their names because different architecture may have different naming. And for this, they called query key and value, and I just called them. But as I said, the original model parameters are frozen, but we have a classifier layer. So this does the last classification operation and outputs a prediction, phosphorylase or not. So this needs to be trained as well. So but if we don't set it, this will be frozen. That's why there's a argument called modules to save. We can define classifier as trainable as well. So rather than training only these LoRa parts, also classifier will be trainable. And why this is called modules to save? Because we don't update any original model parameters. During training, we don't need to save whole model because sometimes models are very big and takes a lot of storage. So now we don't have to save all of the model. We just can save LoRa, the LoRa A and LoRa B, LoRa matrices, and this additional trainable layers, so that if we want to use it later, we just load this small file that has these LoRa matrices and use them. So you can think it like using ESN2 for 10 different downstream tasks and saving these LoRa matrices into a file for different downstream tasks. And for example, you want to use it for phosphorylation prediction. You just take the phosphorylation prediction weights, LoRa weights, and convert your model into LoRa model, which is trained before. So that, I mean, this is very easy to use. For example, for some companies, for different customers, you need to train different models. So storing these models are, can take a lot of space. So you can just store these LoRa matrices for different customers. You can think like that. And also, if you want, you can just apply LoRa to the last layer, not all the layers. If you don't define layers to transform, it applies LoRa to all the layers. But for example, sorry, let's look at it. So the first 5 layers, it has 6 layers. First 5 layer does not have any LoRa in it, but the last layer, the 5th layer, has LoRa matrices so that we can train them. And these are all hyperparameters and can change the newly added parameters and model performance. Let's use this configurations. And the most important thing is, of course, the number of parameters. So the memory consumption. In the full model fine-tuning that we did in the last section, it has trained these all of the model parameters, and it's almost 8 million for this model. But for LoRa, we have injected new trainable low-rank matrices, which its size is this. And so this increased total number of parameters, but only 3.5% of them are trainable. So we are going to calculate gradients during training, and these gradients are only calculated for these trainable layers. So this applying to LoRa will decrease the memory consumption a lot. So it helps us to run these models on smaller GPUs. But this may reduce the model performance. Let's look at it. Is it reducing or not? I'm going to use the same trainer part, so that I'm just going to initialize trainer with LoRa model instead of the full model. So we can think it decreases the performance a lot because we are just training a few parameters, but usually LoRa can have comparable performance with full fine-tuning. So, but using significantly lower memory consumption. So this is very good actually. So as you can see in the model, the validation performance, and in the, let me run the test set performance. It's 90% of accuracy and F1 score. So it was 93 for full fine-tuning. This decreases the performance a little bit, but we used significantly lower memory consumption here. And it's a little bit overfits, but usually LoRa helps preventing overfitting problem because we don't update all of these parameters, just small ones, and these may be generalized well rather than full fine-tuning, which is which can be memorize your training set more. But if you have a lot of data, or you can apply hyperparameter tuning to prevent overfitting as well. This is it actually. So I have added these comparisons here, but I think because of the randoms, it's a little bit different. But as you can see, we have a comparable performance even we have applied the LoRa. So this is the end actually. If you have any question, I will be very happy to answer it.
Thank you, Mert.
I cannot, welcome. I cannot see, I think, the Q&A part, but
I will direct the questions to you. So the first question is, what is the minimum acceptable percentage of model accuracy?
Actually, this can change to task and also can change to data, because here in this task for this demo, we have used a balanced data set, 5,000 positive values and 5,000 negative. But in real life, these data sets may be imbalanced. So looking only to accuracy does not mean sometimes anything, because usually we have, for example, if we have a lot of positive values and our model just memorize predicting these positive values, the accuracy may be very high. Also, these F1 scores or some other techniques are used for balancing these, and can be used to evaluate our model performance for these kind of imbalanced data sets. These performance scales can be changed test to test. So sometimes 40% can be acceptable, but sometimes we need to pass the 90%.
Thank you. I think there is no other question left. So thank you for the demonstration.
Yeah,
so
you're welcome.
to thank all the speakers for great talks and also implementations. And I would like to thank all attendees for their active participation. So tomorrow you can join the training using the same link. And I would like to remind you that the hands-on session titled in Modeling Large-Scale Social Data will take place tomorrow. So as you know, we have provided a limited number of accounts for the hands-on sessions due to the capacity constraints, but all attendees, even without training accounts, are welcome to follow the hands-on sessions. And before the hands-on sessions, there will be also an interactive session on HPC technical support for hands-on, specifically for those with training accounts. So I guess we can end the training for today. So once again, thank you all. Have a great day and goodbye.